There's also a geometric interpretation to complex numbers. If you take a complex number and you write it in this form, the Cartesian form, a plus bi, you could think of the two values a and b as the coordinates of a point in a plane. We're going to label the complex number as a point, always putting the real value as the first coordinate and the imaginary point as the second coordinate. You're going to take the x-axis to be the real axis, the y-axis to be the imaginary axis, and then you'll put your point on that plane. And this will be the representation of your number. If you now introduce length, then you can take that same point, real axis, imaginary axis. You've got a value there, a and b. You can imagine drawing a line from the origin to your point, and we'll put this value as an r. We'll put an angle here, and then we can form a right triangle. We know that that one side is a, second side is b. R is the length here, but we're going to call this the size or the magnitude of the complex number. And just by Pythagorean theorem, it's going to be a squared plus b squared, all square rooted. Sometimes we write r as the absolute value or the magnitude of z. This value inside the angle, this is called the argument of a complex number. And just from using trig, you can find that the tangent of theta is going to be opposite over adjacent, so b over a. Now you've got a relationship here that says if you know the Cartesian values or coordinates of your complex number, you can put it into this form with r and theta, called the polar form. From this right triangle, you should be able to see that the sine of theta is b over r and that the cosine of theta is a over r. So now I can switch it the other way. A is going to be r times the cosine of theta, and b is going to be r times the sine of theta. The complex number z is a plus ib. I can now write it as r cos theta plus I r sine theta. I is just a number. All of our usual rules of algebra apply. So this is what's called the polar form of a complex number. It's in terms of r, the magnitude, and the argument. Without proving it to you, there's something called Euler's formula. If some of you are in Calc 2, you're learning Taylor series, you can prove this formula using Taylor series, but we're just going to accept this as fact for now. Anytime you have cos theta plus I sine theta, you can write it in this exponential form. So another way to represent a number is polar form, r times e to the I theta. And we like this because it allows us to use our rules of exponentials. If you have polar and you want to go back to Cartesian, then you've got these relationships. A is r cos theta and b is r sine theta. You can start thinking about numbers using the complex plane and the polar form. So if I give you the number I is going to have coordinates 0 plus 1i. You can think of it as having a length and an angle. R should end up being 1. The real part squared plus the imaginary part squared is a 1. And theta, you could calculate as the tangent of the imaginary part over the real part. Well, that's undefined, and it's clearly undefined at pi over 2. So this number, z is I, could also be represented as 1 times e to the I pi over 2. The number 1 you could think of as living on the x-axis or the real axis right here. The angle could be 0 or 2 pi or any version of this. So z equals 1 would really be e to the I 0 or e to the I 2 pi or any one of them. A complex number could have infinitely many polar representations. That's kind of a quirk of complex numbers in polar form. You can do things that are a little bit more involved. So for example, you could take a number like this. Z is negative I plus 1. If I were to think about this in the plane, I would have coordinates negative 1, positive 1. So I could think of a r and theta. R is very easy to calculate. Negative 1 squared plus 1 squared is root 2. That's the length or the size of this number. Tangent of theta, the imaginary part over the real part. So is negative 1. Tangent is negative, in this case in quadrant 2. And I already know that I'm in quadrant 2. I can see that geometrically. in order to help us find the value of the angle, I need something called the reference angle. The tangent of theta is going to be negative times the tangent of this reference angle. If you have a 1 and a 1, this angle here will be pi over 4. The tangent of theta, when it's in quadrant 2, that angle has to be 3 pi over 4. And so this complex number, negative 1 plus I, has a polar representation. Root 2 times e to the 3 pi over 4. Of course, there are infinitely many. You can take any 2 pi multiple of that and get to a result. These numbers all kind of work nice because their arguments are special. Sometimes it doesn't work out that way. In this number, the magnitude is going to be square root of 41. And if you wanted the argument, you'd have tan theta is 4/5. So theta would be the inverse tangent of 4/5. That's about as nice as you can write it. Please, please, pretty please do not write this as a decimal, but you can just generically write it like that. Polar form is nice because it allows you to do multiplication and division and powers very easily. So if I give you r1 e to the I theta 1, z2 is r2 e to the I theta 2, you want to multiply two complex numbers, you can assume that all of your rules of algebra still apply, which means that if you have two exponents with the same base but different powers, you can combine the powers according to addition. So you'll get e to the I theta 1 plus theta 2. So the magnitudes multiply, but the arguments add. If you're going to do division, z1 over z2, rather than adding the arguments, you are now going to subtract the arguments. E to the I theta 1 minus theta 2. So very, very easy there. And powers, z to the power of n, you're going to take some complex number and raise it to the power of n. The magnitude gets raised to the power of n, but the argument, that just becomes a multiplicative factor, I n theta 1. If you wanted to, you could write this in full trigonometric form. This would be cos of n theta 1 plus I sine n theta 1. This is called de Moivre's formula.